Okay, now I get this. And we want to reduce this thing to the identity. Now, when you reduced it, you had a 1 here with zeros, and then you had a 1 over here with zeros, and then you had a 1 over here with zeros. Okay? You didn't reduce it in the right order, and you made a mistake. You just left out a part of one of the rows. Now, I really recommend that the process just be, you get a 1 here, and then you wipe out everything below it. Then you get a 1 here, and wipe out everything above and below it. Then you get a 1 here and wipe out everything above it. You move across, one column at a time, getting everything in the column except zeros with a leading 1. Now, sometimes it might happen that when you eliminate whatever was in this position, you might actually eliminate this one too. Okay? So that could happen. But you have to deal with it. So practice that just a little more. Anyhow, you end up with this. Now the big point here is, number one, make sure you do the reduction right, because neither of you is consistently doing reduction in that order. And it always leads to confusion. Okay? We see that, well, this is going to translate the equations, okay? Now I can look at this and say, okay, the equation is going to transform to give C4 as this free variable. C4 being a free variable means we can let it be 0. We let it be anything, okay? So if we let C4 equal 0, it means we didn't even need this vector. And we still got solutions for C1, C2, and C3. Let's write out the equation so we'll show you we see this. Okay? So this translates back into C1. And I'm not sure all my arithmetic is correct over here. Okay? I think it might be. But whether it is or not, that can easily be correct. Okay? And it doesn't really matter for what we're trying to show. Except our conclusion might be wrong if I screwed up the reduction. Okay. So we get C1 plus C34 equals 2 times whatever x1 is minus whatever x2 is minus whatever x3 is. Remember, x1, x2, x3 can be any numbers. Okay? Second equation tells us that C2 minus 2C4 equals x3 minus x1. And finally, C3 minus C4 equals x3 minus x1 minus x2 plus x2. Okay? Okay, well, there are infinitely many solutions because C4 can take any value and we'd still have a solution, right? If C4 is 92, okay, we'd have a negative 92 here, which would be added over here, we'd have C3, right? And we'd have negative 2C4, okay, it'd be negative 184. Added to this gives us C2, right? So if we know x1, x2, and x3, we can find C3 and C2, and also here, okay? 3 times what I say, 94 and 92 is 92. 276, negative 276 over here, and with the values of x1, x2, x3 gives us C1. So we could have expressed this thing as a combination using those values of C1, C2, and C3, letting C4 be negative 94, negative 92. Okay? Now, even better, we could let C4 equal 0, in which case this totally disappears, and we see that we can express this vector in terms of C1, in terms of the first 3 vectors in the set. Okay? So, it looks like we have a redundant vector, right? And that tells us what? It tells us that this set of vectors spans R3. Because we've just shown that there's a linear combination of these vectors that equals an arbitrary vector in R3. This could be any vector in R3, and this shows us we can always find C1, C2, C3, and C4 to do that. Okay? And there are infinitely many possible combinations, C1, C2, C3, C4, because C4 can be any of the infinitely many real numbers, and we get a solution. Okay? That's important to understand all that. Okay? So, write it out. So there exist these constants for any value of C4, infinitely many combinations. In particular, there's a linear combination for C4 equals 0. What I'm saying is, since there's a linear combination for C4 equals 0, well, that linear combination would just be C1 times the first vector plus C2 times the second plus C3 times the third, okay? Plus 0 times the fourth. You don't even have to write that down, so that we see that there's a linear combination of these three that equals this, okay? So, and that happens only for C4 equals 0, because if C4 isn't 0, then you have to have a multiple of C4, okay, of the fourth vector, okay? Meaning, it only occurs for C4 equals 0. So this set C1, C2, C3 is unique. There is exactly one set C1, C2, C3 does this for any arbitrary vector in R3, okay? That uniqueness, the fact that there's only one possible set of C1, C2, C3, C4 for any given vector, tells us, is equivalent to saying that these three vectors are linearly independent in this set, okay? In this space. But now we're going to prove that the vectors are linearly independent, that these three vectors are linearly independent, okay? So let's get to the idea of linear independence a little more clearly.